Alright, so this is my homemade vacuum chamber. It's pretty big. I just got done making it, and it is interior volume wise, it's 11 inches by 11 inches by about 10.5 inches, and it's made of these 3/4 inch acrylic sheets. So I glued those together with acrylic cement, and then I made a gasket on the top with some RTV silicone. I used some mold release on the top to be able to get the top off. So the gasket is formed to the bottom surface of the lid. And the lid, as you can see, it comes off. And then it actually is a very good fit on the way down because I have about 1/4 inch of extension below the lid so that the pieces have something to push against. But when this thing is under full vacuum, each side has about 1,500 to 1,700 pounds of force on it, which is pretty significant. Yeah, that's kind of what drove the design for the thickness of the walls, is because it just takes so much force, and then acrylic is also really prone to cracking. So it's pretty thick, to flex by about 1 millimeter or so, which is significant enough to kind of affect the gasket. So I had to kind of custom make the gasket so it actually is higher on the corners to let the lid kind of flex as it pulls vacuum and still maintain sealing. But it works pretty great. It pulls down to like 0.02 bar, 0.01 bar, which is pretty good. Could definitely boil water. And right now, this is like my first demo. I have it set up to do this experiment where we, the classic vacuum versus atmosphere experiment of dropping things. So we're going to drop the piece of paper in atmosphere. You can see it's fully pressurized now. And then we're going to pull down to vacuum, and we're going to drop the same piece of paper, and you'll be able to see how the lack of air pressure and the lack of air density affects the falling of an object with a really big surface area to mass ratio. So I'm going to drop it here. I have a magnet holding the paper up against the top. I'm just going to pull this big magnet away, and that should release the paper. So 3, 2, 1. You could see how it definitely kind of felt the air, kind of flattened out, and took a bit of time to drift down. So now we're going to pull this thing down to full vacuum and repeat the experiment. So we'll close this valve, open this valve to the vacuum pump, and start it up. I'm going to put in the earplugs right now because I'm still kind of testing it, so if it implodes I don't want to lose my hearing. The thing takes about 1 minute to 2 minutes to pull down, and even longer depending on if you want to go completely to complete vacuum. To get about 0.95 atmospheres, it's about 1.5 minutes, but if you want to pull down to as low as it can go, it could take 3 or 4 minutes. That's just because it's a really cheap vacuum pump, and I kind of skimped on that, which is okay. I'm not really looking for extremely fast performance here, but it does take a bit of time. Okay, earplugs out since it's done pumping. So like I said before, this thing has about 1,500 pounds of force on each side, just from the weight of the atmosphere, which kind of goes to show you how much of an effect it is. People don't really realize that the air weighs so much, but it does. So I'm going to take the magnet off, and you can see how the paper drops now. 3, 2, 1. You can see it was much faster, and the paper didn't really inflate that much, which is cool and expected because there's no air in there. It's almost a complete vacuum. So now we're gonna repressurize it and yeah.